Okay, so after learning about how to normalize a vector or what the inner product represents, what exactly is the interpretation for inner product, let me give the definition for the norm of a state. As in the beginning video, I have made a mention, anything that is enclosed in a slash and a greater than symbol would be called as a get or state. Of course, vector notation, all of us know, but to differentiate between a the classical notation and the quantum computing notation, we use this notation of ket or state. Okay, let ket xi be given. Of course, ket xi be a state, something like that. Then how do I find the norm? Is like our usual norm only. The notation is like our usual norm. The ket is enclosed in two parallel lines, and then it is nothing but the root of the inner product. Suppose if I have to normalize a state, then how do I normalize it? Is the state by its norm gives me the normalized state of a vector. Okay, so after this brief definition or introduction, let's do some problems so that we are clear with the things. Now, here I am being given ket xi and ket phi to be two vectors. Directly they are being given, not in terms of the notations of the qubits. Of course, you can rewrite them in terms of qubits as well. That is, ket xi, I can as well write it as 1 by root 2, just to make hands free. 1 into ket 0 plus 1 into ket 1. I can write it like this. Okay. And then ket phi can be written as 1 by root 2 is common to both. 1 into ket 0 plus, of course, minus 1 into ket 1. I can write like this, right? Okay, leave that. Let's see certain things that are being asked in the question. I'm being asked to find the inner product between phi and xi. So I just split it so that my things are easy. Okay. So I know how to write this as a vector, ket phi. The dual of ket phi is what I will write. That would be 1 by root 2, 1 minus 1 into 1 by root 2, ket phi, 1, 1. Okay, 1 by root 2 into 1 by root 2 gives me 1 by 2. Of course, multiplication of this vector, just see what it gives me is 1 into 1 minus 1. It is 0. Inner product between two different kets is 0. Of course, I can check the inner product between he is asking in the question whether they are orthogonal or not. Obviously, inner product is 0 from the definition of orthogonality. Ket phi and ket xi are orthogonal. Okay, coming to this thing. The next question, you are being asked again to find the inner product only. Of course, the conjugate of ket phi or the dual of ket phi would be, see, usually we are not used to writing this notation, so we tend to make errors. Make sure such errors are not repeated. 1 by root 2, the dual of ket phi would be 1 and I. Okay, so if I'm computing the inner product, that's nothing but just split it again. So 1 by root 2, of course, it becomes 1 by 2, 1 and I, and then 1 and minus I. No, 1 by root 2 and 1 and I, which is nothing but my ket phi. Okay, of course, 1 by root 2 is there for this as well. So it is 1 by 2. 1 into 1 is 1. I into I is I square. Again, it is -1. So this is 0. Again, I can say both are orthogonal. Okay. Yeah. Now just see this. Find the general expression for the inner product of ket phi and ket xi, ket xi and ket phi. So how do I find it? Inner product. Okay. So as a vector, this one would give me, this is nothing but, this gives me something like C and D. Okay, so this is nothing but C and D transpose. This is the row vector. Okay, so CD and this is AB. So I'll be getting AC plus BD. Next, how do I find the normalized states of ket xi and ket phi? That's the next question. How do I find the normalized states? I divide by their norm. So for which I'll be finding the norm. How do I find the norm? This is the expression for norm. And then what does it symbolize? What does this symbolize? Is to split it. So what are the values of the norms that I'll be having is the dual of ket xi would be nothing but, just see the notation, how I'll be writing the dual. 3 bra 0. Of course, -2i is there. So conjugate of it is +2i bra 1. Okay. So if I write it in vector format, what about the expression for this in vector format? 3 and -2i is the vector format. So this would be 3 2i plus 2i into 3 minus 2i. So what does this give me? 3 is 9 plus, why? Because I squared is -1. 2 into -2 is -4. So minus of minus into minus is plus. So it is 4. It is nothing but 13. So how do I normalize ket xi? Normalized ket xi would be something like ket xi by norm ket xi, norm of ket xi. Okay, I'm writing this notation only. Of course, I can write as well like this. Ket xi by norm of ket xi is nothing but under root of inner product of ket xi. Okay, so what should I be writing? Three. Ket xi is nothing but 1 by root 13. Ket xi is nothing but 3 minus 2i. This is equal to 3 by root 13 minus 2i by root 13. Okay, this is how I normalize ket xi. Of course, you can go with finding out normalizing ket phi as well. Ket phi is ket 0 plus 5 ket 1. Okay, I can just write the vector here. Ket 0 is 1 0 and then 0. So it is nothing but 1 5. Ket 1 is 0 1. So it is 1 5. So its inner product would be 1 into 1 plus 5 into 5. Inner product is 11. Inner product of, I'm just writing here 1 5 and 1 5. So it is 1 plus 25, so 26. So this would be 1 by root 26 into the vector 1 5. Of course, I can take it inside and write the remaining thing. This is all about inner product. I think with this small little problems, the concept of inner product is clear to all of you. Okay. And how do I normalize a vector? That is also clear. Norm is nothing but the root of the inner product. Okay. Of course. Now, immediately after inner product, the next thing that we should talk about to make things obvious is the outer product. Obviously, how inner product looks, uska ulta will be outer product. Okay. So, how do I do that? How do I write it? It's just the ulta, like how I'm writing my dual. Dual, how am I writing? If the ket is like this, then its dual would be ulta, uska ulta. Of course, if it would have been like this, then its dual would be something like this. So obviously, notation with the outer product also, because one is inner, the other is outer. Things are like that only. But what are the resultants of outer product? There is a variation compared to the inner product. It's the product of two quantum states, obviously, in the form of which results in the form of transforms and operations. Now, outer product results in many things, okay, which we will talk in the coming videos to go. Form of transforms and operations on a Bloch sphere. Again, regarding the Bloch sphere, I'll make some separate video on it, explaining things on Bloch sphere. Obviously, mathematically, what outer product represents is the is a matrix. Now, here what I'm getting is a number when I'm going with the inner product. Outer product results in a matrix. Now, how do I represent outer product? As I have said, it looks just like the ulta of the inner product. Okay, but what exactly it signifies and all the things we'll learn. Okay, suppose if I'm going with inner outer product for the same vectors only, I can find out outer product ket xi and ket phi. What are ket xi and ket phi? Ket xi is nothing but my 3 plus phi I and some 9 that I've considered in the previous video. You can just check. Ket phi, of course, is nothing but 5 and 7. Okay. Yeah. How do I find outer product? Let's see. So that there are no doubts when I use this notation. Okay. Now, obviously, I have this, and if I separate this two, just see guys, what it represents. Ket xi. I have it here, right? Now, what is this? If I separate this two, it's not, of course, I'll put a dot here, signifying that it's just the product. Okay. So what is this? It is nothing but the dual of ket phi. Okay. What is dual? It's the conjugate transpose when there are complex numbers. If there are only real numbers, then it is just the conjugate. It's just the transpose. I'm sorry. Okay. So just see here. Once I rewrite like this, things become very simple. 3 plus 5i, 9. I'm just considering ket xi as it is. It's the dual of ket phi. So I'm considering the conjugate. Just the conjugate transpose, just the transpose, because I have only real numbers. I think I am clear and I'm not confusing. So I can just clearly see, guys, there are 2 rows and 1 column. And here I have 1 row and 2 columns. So obviously 2 rows, 1 column and 1 row, 2 columns would result in a 2 by 2 matrix. I'm clear of my output. Okay. So 15 plus 25i. Okay. And then 21 plus 35i. And then 45, 9 5s, 45, right? 9 7s, 63. Okay. This is the resultant of a outer product. I think I am clear. Okay. How do I find outer product? This is how I find outer product. Of course, when I'm talking about outer product of certain things, they symbolize, they give different outputs, or they symbolize different things, which I will talk about in the coming videos to go. But then again, guys, quantum computing has a lot of basics on linear algebra. Takes many basics from linear algebra, of course, from matrices. And then when I'm talking about matrices, all these things, matrices and vectors, normality, orthonormality, orthogonality, linear dependence, independence, all those come into picture. Now, I'll talk about linear dependence and independence of the kets also. But then what is most important is the eigenvalue, eigenvector property. Eigenvalue and eigenvectors in quantum. Eigenvalues and eigenvectors. How do I find? Similar way in which how I was doing it in matrices. Okay, suppose if I am being given some matrix, something like, I'll just write a matrix 0, 1, 1, 0. Of course, this is a matrix, this is an operator. Of course, this is a gate also, the famous gate of quantum, Pauli X gate. Of course, you can just see here. I'll just make some points. I'll just stress on some points. That is, if you see the column vector, it looks like my ket1, first column vector. The second column represents my ket0. So X gate is nothing but the flip of, actually ket0 is the first one, ket1 should be the second one. It's a flip of states, I can say. Why? Because there are many more gates, guys. To remember all of them, there should be some shortcut. Flip of states. What are those states? Ket0 and ket1, they have been flipped. First ket1 has come, then ket0 has come. Then how do I find the eigenvalues and eigenvectors for the Pauli X gate? Let it be X, guy. Of course, I'll give it some notation like U, guys. Okay, U or U naught. U naught is the notation. Again, why U naught? I'll talk about all those things in the coming videos to go. But here, how to find the eigenvalues and eigenvectors, let me talk about. How do I find eigenvalues and eigenvectors? To find eigenvalues, I'll be considering det A minus lambda I is equal to 0. Of course, all of you know, I have a system of this format where a matrix is represented just with a small scalar like lambda. And then this is the relation Ax is equal to lambda x. Now, if I take lambda x towards the right, Ax minus lambda x is equal to 0. And then if I take x common, which is there in both, A minus lambda. A is a matrix, lambda is a number. So I cannot subtract the number from a matrix. So I'll be using the identity, that is the identity matrix, like the one in numbers. I'll write like this. Now this is a homogeneous system. This is a homogeneous system. For a homogeneous system to have, homogeneous system is always consistent, guys. Consistent matlab always has a solution. Has a solution. Why? Because if I take x is equal to 0, 0, 0, 0, always LHS and RHS are satisfied. So unlike a non-homogeneous system, homogeneous system is always consistent. But then x is equal to 0, 0, 0 is a trivial solution in which I am not interested in. So using determinant method of finding rank, to have a non-zero solution, the rank should be less than the order of the matrix, or in other words, determinant should be 0. Determinant should be 0 means what? Determinant is, suppose A is a matrix of order 3 by 3. Determinant is also of order 3 by 3 only. Okay, or determinant matrix is also order 3 by 3 only. Now, if this order is less, means what? If the determinant goes to 0, then what happens is all the minors of order. Minors means what? Of order 2 by 2 or 1 by 1 will be there. Okay. So those, if any of those minors are non-zero, then the rank of the matrix will be 2. Of course, it will have a non-trivial solution and all those things for a homogeneous system. So here, what I'm trying to stress here is determinant method of finding rank says to have a non-zero solution for a homogeneous system. Homogeneous system is always consistent. What that is just look here. Suppose if I have something like this, 0 minus 1 0 0 0 minus 3 or something like this, and x y z, this is equal to 0 0 0. Okay, this, suppose if this is the system that I have. Okay guys, a minus lambda I has given me this, into x has given me this. So now if I put it in equation format, 2x is equal to 0, minus y is equal to 0, minus 3z is equal to 0. What happened? Rank is what? Rank is 3. Rank is 3. Okay. Also, when rank is 3, what has happened for a homogeneous system? All the variables have gone to 0. Suppose, see guys, suppose if the rank is less, if row is not 3, it is 2. Okay. Then what happens? First equation, 2x is equal to 0. That implies x is equal to 0. Y is equal to 0. Fine. But there is no information about z. So I can take z to be some non-zero value, some k or something like that. So my vector would be 0, 0 and k, or 0, 0 like this. Okay. So only if the rank is less than the number of unknowns, a homogeneous system will have a non-trivial solution. If the rank is equal to number of unknowns, then the system will not have, homogeneous system will not have a non-trivial solution. It will have only trivial solution. Trivial solution where all zeros are there, I'm not interested in. So for a non-trivial solution to exist, delta minus lambda I should be 0. So I should be considering for eigenvalues that a minus lambda is equal to 0. Many of you know it. In case if someone doesn't know, for them, I'm just stressing on. Okay. Yeah. So 0 minus lambda is minus lambda. 1, 1, 0 minus lambda is minus lambda. This is equal to 0. Okay. So what do I get? Minus or lambda square minus 1 is equal to 0. So eigenvalues are lambda is equal to plus or minus 1. Right. Now, accordingly, I'll be going for finding out eigenvectors as well. Now here my eigenvector would be something like this. Eigenvector would be something like this. Okay. So u ket xi is equal to lambda ket xi. Okay. What's my eigenvector? I'll, of course, you remember the superposition in the last video. Superposition way of writing ket xi is alpha ket 0 plus beta ket 1. So alpha comma beta is what I will take here. So what happens? U is nothing but 0, 1, 1, 0 into alpha beta. This is equal to lambda is equal to 1 is what I am taking here. So what I'll be getting? Alpha beta. Of course, this is all the stuff that you have in matrices, guys, is just a recollection, right? So what I'll be having? 0 into alpha. Beta is equal to alpha is what I have. First equation. Second equation is alpha is equal to beta is what I have. So what can I say about the eigenvalues? Alpha is equal. I put one on the other. So what I'll be getting is both are equal is what I'll be getting. And then this is the way I'll be finding eigenvalues for the matrices. Okay. If alpha is equal to beta, what can I say about it is I can write ket xi as, instead of alpha beta, both are alpha only. Let alpha is equal to k1 or something like that. So I'll be having 1, 1 into k1. Okay. That's how I'll get one eigenvector, ket xi1. Let me call this to be ket xi1. Okay. For lambda is equal to minus 1, I'll be taking u into ket xi2. This is equal to minus ket xi2. Okay. So what I will be getting is beta is equal to minus alpha, or alpha is equal to minus beta, either of them. So, if alpha is equal to K2, then Ket xi2 would be what? 1 and minus 1 into K2. So, this is one eigenvector, this is another eigenvector. Remember, this is my Pauli X gate. Of course, if I am saying X, there is a Y, there is a Z as well, about which we'll talk in the next video. This is all about finding eigenvalues and eigenvectors for quantum states. Thank you.